Yeah. Okay. So, hello everyone. Welcome to this term's last QCDG. So our speaker today is Karl, who's going to come talk to us from Southampton. And before we get started, let's do a usual round of introductions. I'll kick it off. I'm Andrea. I'm a junior research fellow here in the department working on quantum computing for quantum algorithms.
Hi, I'm Duncan. I'm a research scientist at Continuum on the corner. I have a background in GFT, but now I think about how to do quantum simulation for more. Hi. You have the team at the Continuum. Coordinating all things.
Hi, I'm Alex. I'm professor of theoretical chemistry. Still sounds very new. I guess I do quantum algorithms for computing and other quantum chemistry.
Hi, I'm Kieran. Work also at Continuum in Quanto, which is our product for doing quantum simulation.
Hi, I'm Salah. I'm a PhD student. Working on design, scared of quantum algorithms.
Hi, I'm Griffith. I did visualics, and now I'm a research scientist in Continuum, looking at various favorite things and details.
I'm Rowan. I'm a PhD student and was doing an internship working at Mexico in spin over coupling.
From Dylan, I'm a PhD with Alex, so I know all of things, CI and those.
I've been a master student with Alex, a student from computing. I'm a chairman of the PhD student with Conway.
I'm Karl. I was in my PhD with class, and also now research out with the London, and I look at that one investigation.
I'm Warren, quantum algorithm developer at chemistry buildings, also strength diversity used to quantum regression and just stuff. I learned I'm James. I'm a student in the integrated condition exploration in the engineering department.
Right, great.
Oh.
For the PhD student in various groups, and I did essay for publishings.
Thank you, everyone. Okay, so that's me. Okay, so I'm a lecturer in Southampton, and I'm also assistant professor in Denmark. And I'm going to talk about a bit about the title, but I like alliteration. So I naturally think quantum chemistry algorithm, quantum computer problems, prospects. So I look at, well, one thing we look at is obviously quantum algorithms, but not in terms of quantum startup or more like academically. So I might say critical thinking points. You're allowed to challenge me. No, I'll challenge me by say creating things, doesn't matter. So yeah, what I'm going to talk about today is interesting problems in some prominent quantum algorithms in chemistry and interesting problems to me. So that hopefully a little bit overlaps with what you find interesting. And what I chose to read. So we worked on QSCI, literally of course, and then stuff methods. And he starts also from like current to near term, turning from here. I'm sure to think in these terms. Right, let's get this out of the way. We start with quantum QSCI. So what is this? It's basically QSCI method where the sampling of the configuration is not done on the quantum computer, but it's done on the computer. And basically, whenever you see something done on a quantum computer that has something to do with chemistry, it is quantum QSCI or SQD. So it was originally called quantum QSCI in 23, and then IBM renamed it to SQD, but it's basically the same thing, and it has great headlines, and it's like probably it is the only algorithm in chemistry that actually run reasonable size stuff. Use a quantum computer to run reasonable size. Okay, so how does it work? You start out with the computer and you prepare somehow your ground state, some kind of ansatz. And then, as the name says, you are sampling determinants. So that means you have your ansatz, you're not measuring any complicated operators that you have to do like unit transformations. No, you take it, measure in the computational basis state, you get out your ones and zeros, and they directly correlate determinants. Which is great because it allows you trivial and very effective post-processing. Because that means you can determine it out, and it will have to have the same number of alpha and beta electrons. If it doesn't, the quantum computer does not exist. So this is very nicely scalable, effective, and trivial post-processing. You can do on every single measurement that you can't normally do. What do request operators? And then you have your determinants from the quantum computer, then you chuck them into your favorite classic SCI solver, then does the bulk of the work. It's union, it brings the CI matrix, and then a stabilization. The stabilization is the computation. Basically, you have this quantum sampling, determinants, and you chuck them into your CI. And that, of course, is very much lean from chemistry. For example, in deep path CI, you are whole sampling. You're sampling, for example, like this, where you find connect determinants I to already included reference J via the Hamiltonian matrix in its state, and if it's a certain threshold is exceeded, you get this determinant. Now this is kind of that exists for a long time. This is everything. So when we looked at this, and I always had picture of people who also Peter. The question is outsourcing the sampling to the quantum computer actually improving select CI? And that's something looked at 1.5 years ago, almost now. And you get this. There are some limitations I think one has to think about if one wants to actually do this. First important thing that's very trivial for anyone who comes from quantum chemistry, but not necessarily from quantum computing, is that this is an exponential scaling method. This is a method that does not have this exponential reduction you have from other quantum chemistry and quantum algorithms. It's this construction. This is the CI matrix. More accurate. So that's kind of how it is. And this is of course a problem because
48 cores. That happens if your CI you want to diagonalize is much less compact. Now you need an actual supercomputer. Now you actually have to call that supercomputing because now you really need a supercomputer to solve. Exactly. You do this, yes, so you do this, you might be able to get up around the efficiency of the sound. Because now for like this determinant here, makes it much higher and not that low, so it will be more likely to turn out. But as you said, what actually is true is it destroys the compactness even more. Yeah. Because now this determinant is definitely useless, but it will be found as likely as one. Yeah. Yeah. So let's say that we do a systematic demonstration that we think. I mean, maybe not. I think this is like, I don't think we will just any justice here. I mean, there's more that. Like the specific thing about it is it determines the mass of most the energy. Yes. Yeah. That's the intrinsic bias. Yeah. Yes.
No,
So my audio, I'm saying here the way.
let me just try one more time. But if none of this works, then that is probably. Yes, and you can hear people. So, okay, I think it's working again. Carry on.
Yeah, let's switch now to VQE. So I don't know if there are other questions on that. Then
I think in more general thing,
Yeah.
I mean, in my mind, it's doomed because it's exponential scaling, and on the classical computing. So do you have any insight as to, other than if you do the classical bit and you do full CI or you do CI in that space, you get a very nice looking number, irrespective of what rubbish you put in. Is there any other reason to do this?
on the quantum computer, I mean, okay. So reason for a quantum computer is if you yes.
Yeah. Okay, fine. So it's top science is going to
I mean, it's the only thing. I mean, that might be a bit unfair of me, but like this, it's just true. Like there's no this, you don't need error mitigation, you don't need error correction, you need nothing. You don't know immediately if something is right or wrong. There's no other algorithm that can do this post processing. And that's super powerful for the machines that we have. So okay, let's go.
So just want to confirm the first one is the hybrid algorithm or
Sorry, can you say again?
is it hybrid algorithm, classical and quantum, or is it pure
Yes.
quantum one?
Well, I'm not sure what you mean. Actually, sorry.
So is it like a classical algorithm developed into quantum version?
Yes. So it's just removing this. This is all a classical algorithm. Removing that part of the classical, substituting with that, and keeping that.
Okay, yes, okay.
Actually, we should have called them much. It's fun because like I always write like this, but actually, I mean, EP was before QSCI, but like in terms of how they came along, so there's much more known about the problems of EP, which is, for example, the choice of answers. What are we doing? How do we optimize this very, very difficult to optimize thing, which you was just hiding the problem classically. Then you have measurement overhead in terms of how often you have to measure. You maybe want to do stuff that's not just a ground state, and you maybe want to try to run on the hardware because we said near term is maybe bringing value, so we should try it, but some problems or some problems I chose. Yeah, the one I want to talk about first is the measurement overhead. It's done. Recent. All right. Okay, so VQE, we know that kind of. If we have in a classic computer, we have our CI expansion. Now we want to create this scale exponentially. We want to create this exponential scaling expansion on our quantum computer with a linear scaling number of qubits and somehow be able at these rotations create this kind of system. And we can do this, we can write it like this, it's a unitary operation. And we can do this in terms of ansatz. There are a lot of ones. These are a few I personally like. You might like other ones. There's like a structurized or disentangling CSD. You can layer this up to get to a full CI expression. You can use TOPS, which is the Hugh Burton who was here. Yes. And these are ones where you say, okay, I fixed the answer before, and now I try to do my global optimization or local. Yes, and then here's the minimization. I'm not going to talk about it, but it's the end of the day. An alternative is adapt VQE, which basically is okay. Instead of saying before and how the layout looks like, we are adaptively building this layout. So I start with a reference, and then I'm adding some kind of unitary and another one, and I see how my energy behaves. And what I'm adding is basically always I have some kind of generator, excitation, I exponentiate it, and this is the unitary I'm adding. And there are various ways of how I express these generators. I can use the fermionic excitations, I can do qubit or qubit-based excitations. They're like the three most cool, and I'm just going to focus on fermionic excitation, meaning it's basically these expressions we have in UCCSD pool. It's generalized singles and generalized doubles. And then with this pool generators, I build my exponentiation, and then I can build an answer. That's the idea of adapt. So the question is now, how do I choose the next operator I want to add? I have some kind of at stage n. How do I create n+1? And there are two ways. So the original one is gradient-based selection. So this generator, if you do your favorite BCH expansion, you will find out that the gradient is just this commutator. And this was done originally, so you can choose the next generator you're adding based on the size of the gradient. Another idea is to use the energy-based selection. So saying I actually look at which operator is lowering the energy the most. These are the two ideas basically. And how does that work? It's also called excitation solves. There are various names in the literature, but basically we know from the generalized parameter shift rule that we can express the 1D landscape in any generator for a given ansatz as this trigonomic expression that depends on R. R is the number of frequency gaps, or it's 1 minus the number of eigenvalues your generator has. And this is, I stole this from Penny Lane. For example, here for like a generator with RS1, which are Pauli operators, for example, you need to measure at 3 distinct values, and then you can do a trigonomic interpolation, and you can actually completely reconstruct this 1D energy landscape. And you can do this for RS2 and RS3, and however many eigenvalues this generator has. And this is the basis of we use in like whenever we calculate gradient on a quantum computer, or when we do an optimization with a rotor-slope algorithm that just sweeps over this. So for our pool, so for an embryonic pool, RS2, so we can express it as these 5 expressions. Important to note, it's only for a general fermionic pool. If a spinnet at the fermionic pool, this number gets very ugly. But we are not doing spin adaptation here. So for that, we can express it in these 5. And that's basically what's done in this sort of select. You want to add a generator, you're measuring it at 5 distinct parameters, shift, then you can reconstruct the landscape, you find its minimum, and now you know how much this generator lost energy, and you know the optimal parameter needed to lower it, which is what people call it the warm start. What's the problem here? It's not really a problem, but in a sense is that the gradient selection is cheaper, but of course it's just approximately lowering. Whereas the rotor select version is more accurate in the sense of just thinking about a single generator, but it's more expensive. You can have a look here, for example, here's 3 systems, and the rotor select is always like a bit more than a factor 2 more expensive to sweep.
Yeah. Do you need to increase the accuracy of your measurements with the more things you need to measure? Because effectively you're something in a landscape that's just constantly going up and down. And if you knew the numbers exactly, then you would be able to invert that and do that exactly. But as soon as you have noisy measurements, then who knows what big of the landscape you're sampling, and the error bars get very large.
That is true. So we're looking at this. So I'll come back in a few years and I'll tell you. But no, that is true, because actually, yes. So once you have shot noise, for example, you have to be a bit clever how you do it. There's one paper about this. So basically now you want to probably do it in like a multilinear regression way, where you take into account the spread in the standard deviations. Yeah, seems to not have this problem.
Yeah,
which has to be worked on.
Did you do this more efficiently? You kind of know the shape of the function, so you're fitting, and you only need a few empty evaluations. If you evaluated gradients, can you do it more efficiently by fitting?
So that is what I showed is literature.
Okay.
The actual talk is about how to do it more efficiently. Give me a big slide. Sorry.
Sorry.
Yeah. Yeah. So some people have told me, why don't you do it more efficiently?
That might be really.
And that is what was said by Manuele. And that's the reason I wrote it also like this in the beginning, because basically it starts with thinking about, okay, so this equation is for any theta. You do this, you can do any theta. Doesn't matter if it's the first, the second, or the one that sandwiches your Hamiltonian. But of course, in the rotor select, you're actually only interested in what you add next. So we start out by thinking about this as a transformed Hamiltonian. And we know that the transformed Hamiltonian like this, we can basically always write as some kind of infinite sum over commutations. This, of course, is not helping us if we have to do this. But there is this work by Francesco, where basically he has shown that for specific generators, if they transform some kind of operator, you can write a closure relation that only consists of these 3 terms. But these 3 terms depend on some kind of alpha value. And this alpha value is basically, okay, you have to go through the second condensate mass, but you will figure out that basically there are 3 ways to do this. You have 3 cases. You have an alpha 1 case, alpha 4, and an alpha 0 case. which depends on how exactly your generator transforms some kind of operator. And that's really important. The important thing is, if you know it, if you know in which case you are for a given operator O, you can actually find this transformed closure as only having only 3 coefficients. That's kind of the digested version of it. And if you do this, so the idea is basically, okay, instead of we add a generator, and we have our Hamiltonian, which is just a sum over a lot of operators that are all similarity transformed. And so basically, we are able, we can just split our energy into exactly 3 contributions. That will be the contribution of all Fermi strings that transform like this, and like this, and like this. And then for each of these, we can write down the relations. And we can see, okay, for the 0 case, that's very trivial. For the 0 case, alpha is 0, so these terms vanish, and you only have this one left. And for the alpha 1 and the alpha 4 case, you can basically see that all Fermi strings in the Hamiltonian, that are for 1 case, they can be expressed like this. So this is now a 1, 2, 3 parameters, and for the 4 case, equally, there's only 3 parameters. So it's a very diagram. So basically, take a Hamiltonian, you know it's a sum of Fermi strings, you have a given generator, you now have to evaluate, you have to figure out how each Fermi string for a given generator transforms in terms of these 3 values, and then you can split your Hamiltonian in 3 contributions. You can do this actually based on overlap in indices, or principle pre-calculated theory. But if you do this, basically now, instead of having a 5-parameter shift rule, you have a 3-parameter shift rule and even a bit less. You can do some other tricks in terms of reusing evaluations. For this, you have to look in the draft, but to simply show. But basically, going back to the table we had, we what happens is this efficient row to select is basically a factor 2 cheaper than the original row to select, whilst being mathematically identical. Like there's no approximation. It's just realizing you're doing a transformed Hamiltonian, and actually, if you would write out the second condensation, you would have seen from the beginning, someone said there's a more efficient way. So it's mathematically identical, numerically identical as well, of course, to check this. And so basically, you pay half the cost for your row to select, and then basically the row to select way comes down to almost the same cost as the gradient-based selection, which is nice. I mean, a factor of 2 is maybe nothing in the grand scheme, but you know, you have to. It's also academic fun, but look at that. But nonetheless, a factor of 2 is nice. So basically, you can now do with this efficient row to select and allows the row to select pool selection at the cost of gradient based. But of course, the cost of gradient based, but you get the actual energy lowering, and you get already the optimal theta. So in principle, what you can say is, oh, I could now just do an adapt without any optimization. So you can say, I'm just choosing a pool, do this like 1 to 3 measurements for each pool. I add this. This has already optimal theta. Now I choose the next one and add this. So in principle, you can create this without doing any optimization, which is, as we write in the paper, look, it's a nice thing you could do if you want to be able to do something on current machines, because no one is going to do your VG on current machines. But that you could do that in principle. So we've done this here. You can see the solution hydride. We call this RSE last because the last theta is always added the exact one. And you can see we have actually 2 things. You can do another clever step. So basically, it doesn't change asymptotic scaling, but of course, you don't really need the singles because you can always fold the singles into your integrals, and then you just have a double pool. And then you are a bit cheaper. It doesn't change decimal scaling, but you're a bit cheaper. And then in terms of you only optimize the last one, you get a bit more. You can also get, of course, another layer of improvement in energies, which is just classic cost. I mean, optimization. And that's the green one. So the green one here is with orbit optimization. and you are double pool, and this is without optimization and a single double pool. But you can see already, like, we got lucky here. That we got down to 10 to the minus 5 without actually, like, if we would not do an optimization. You can see here the classic problem of adapt or any that we get at some point stuck at something that's not very close to full CI. Because this is done is a local optimizer, as most people do it. They're only brave enough to do global optimization of VQE. And this is not one. So we get stuck. But of course, if you would actually optimize, okay, we get stuck. This was wrong of me. Sorry. There's probably also an optimization problem. But also we get stuck because we're adding new operators without allowing them to relax with each other. So if we now allow them to relax with each other, which we can show in red, or we optimize in orange, but in orange we actually get down. So a day of doing adapt without any optimization you can do for like some toy system and use some hydra, we will not feel it broke. But in the end, we actually need to use it.
Excuse me, can I stop you here? I noticed that the two molecules that you build it up linear and geometry. How big is that? Well, how much geometry?
Yes, we have water.
And
We might have done some hydrogen chain. I just a third panel would have made it very small. So I just didn't add in the paper with water as well. But yeah.
Do your pools end up being pretty much identical?
What do you mean? Oh, you mean what is actually like this?
Yeah, no, you end up with at the very end.
Yeah, the final answer.
Yeah.
I don't know. What great question though. Let's say actually, yeah, it's not a good question. So that's good. Yeah, we can look at this. We have looked at it, but I don't remember what the actual ends up. Then I mean this was, I've been told that people ask questions. I just chucked together a lot of slides like any point. When do we end?
I think we have the room until 2, so there's no.
You saw me at some point. And now we talked a bit about switching over. Now I'm switching to different projects, still QE. And the other question was, can we run this? Not even BQE, can you run on hardware like the estimation of the electronic council? And so this is a project of error mitigation. And the first thing you might ask yourself is, why do we need error mitigation? So let's look at this example. We have here the circuit of lithium hydride in a two-reactor space, that and with this ansatz, which has 56 entangling gates. And we are now going to run this on IBM Mumbai. This has been done a while back. And I'm just like using these slides. So this device actually doesn't exist anymore. But it's also, I mean, devices get retired very quickly. So okay. So what are these here? So this is centered at the full CI solution. This is Fog. And this here we can see if we do like sampling, if we have 100,000 shots, we have this distribution where we should end up in. If we have 10,000 shots, we are only here. So higher statistic loss in CPU. This is ideal on the CPU. So this is the correlation energy.
so this is measuring a whole load of powers to get the density matrix to get the UCCSD energy. Is that
Yes, this is using Hamiltonian transforming Pauli strings and then measuring these Pauli strings with supervised commutativity down, but basically then measuring these Pauli strings. In this case, it's now a sampling shot noise simulator. But this is then, if you do nothing, and I mean, essentially how we started just playing around. If you then just run it without any mitigation, you get this. So we got this. It's now probably 1.5 years ago, and this device doesn't exist anymore. But nonetheless, I would not be that much different if you don't do anything. So if you don't do anything, we just run it 5 times. We got these energy results, and you can see we did not fully capture the correlation. But why is that? That is because, of course, these devices are noisy. We have to work on that, and people have to work on it, people have been working on this very, very much. So this is kind of so what's one thing people have done is, for example, error mitigation, just done close in 21. And this is the basis of what I'm going to talk about now. We have extended this twice, so in 0 and type in 0, and I'm going to go through this now. Okay, so what is real error mitigation? This is a very straightforward way to think about how can we combat a problem that what we read out is not actually, for example, we can say we have this 2-qubit system and we prepare a 0-1 state. And if we now measure it, we should, of course, measure the 0-1 state. But because building a quantum computer is a very hard problem, you might not. So you might actually, you measure, you get 0-1, measure, and actually only 90% of the time you actually get 0-1 out. So this idea here in the paper, one was, okay, let's just characterize this before we run our experiment. So we built this confusion matrix, assignment matrix in various ways to say, but basically, before we run the actual circuit with the actual experiment, we prepare all possible quick tricks and we measure them. And we know what the quantum computer is doing to our measurement. We build a matrix and then we invert it. When we do our actual quantum computing experiment, we have all bit strings. We multiply them with the inverted M matrix, and then we get some mitigated results out that should deal with that problem. And I think, of course, if you do this, you do that once, and then this is in principle independent of what answers you then put actually in, and so you measure. But of course, this is a only result. And this also scales exponentially just to characterize it, because you have exponential many bit strings you have to prepare and measure. So this matrix here is scaling exponentially.
To some extent, it's a combination of preparation and measurements. You still, because you might have not.
Yes, that is also true.
And is there a way to deconvolve those further without more magic? Probably magic.
Well, no, that you're right. I mean, in principle, I think there's more. I mean, in principle, I think there's also one to be arrogate under that.
I think most error models treat prepare and read out as a combined thing. Yes, so you can sort of, if you want to play with it, you can put the error at either end and pass it through sort of thing.
So we were thinking the first thing when we played around with that is okay, let's just deal with the fact. Well, I mean, you have to check its condition number, but yeah. If you, I reckon, it's a good question.
Those are probably some probabilities that should be invertible, but any error in them is
That's fair point, yeah. You should take notes. The first thing we did is, okay, if you already have to prepare this ansatz to create this confusion matrix, why not already add the problem that we will later do in the circuit? So in this case, for this M0, so basically, this is our problem circuit, why not? Or FUCCSD or whatever it would be. And we just add this with the theta set to 0, so that becomes an identity. So it doesn't change anything in terms of the readout process, but you have basically an approximate way to encode the gate error. That was kind of the idea, and the rest of the process is the same. Of course, now this process is not Anders independent anymore, but it's independent of the Anders parameter you then actually do the experiment with. So you can do it for the whole of the VQE routine. But it doesn't do anything to the exponential. But small steps.
Is it possible to persuade these compilers to do a game that does nothing?
I have tricks. Yes, you can. You can play with KidsKit and Yeah, the best thing of that job is that I don't have to play with physics anymore that much. It's challenging, but it's also fun. Okay, so let's try this again. Now we do H2. This was done on IBM Torino, which still, I think it's still, yes, you should say it still. 80 entanglement gates. Let's try to its layout. Use this is the QPS. And then we run it. And look at that. That didn't look too bad. So now we had 5 runs of this. And we can see that 2 of them were actually in the confidence interval where we should get the energy in. 3 of them were not, but I mean, we were in the other room when we don't do anything. So that's quite nice. And it's not 80 entanglement gates. That's not too bad. Of course, it takes a long time to run. This is just proof of concept, just academics having fun. Principle, okay. It kind of works. The idea is kind of works. So we were happy about this.
How many shots do you use for build your confusion mix?
Okay. So there will be. Can I answer that later?
Yes, of course.
So there's layers to that.
Yeah.
Yeah. Okay, we haven't dealt with that. This is still annoying. We still need an exponential scaling M matrix. So we ended up at what then was the final project, which is called tile zero. And that says that we are now doing the same process, but everything I'm saying now is only valid for this kind. And that's it. And they are very, they're everywhere. There is, of course, our old favorite one from Hugh Burton. And then there are many other ways where people have done this big layer structure. It's a very common thing because it's nice for the hardware. So the idea here, and this is okay, instead of creating this big M matrix, we are just doing basically a matrix decomposition of each type. We don't need to do everything. We just assume we do a locality approximation, just assume the arrow is local to the type, which is an approximation, but it's not a too bad one if you consider that the tiles are low. And then basically, for example, then each of these tiles is by itself just a 2 to the power 4, a 16 by 16 assignment matrix. And then you just construct your full assignment matrix by this, and then you press this, then you characterize this. And then because in these, especially in the QPS, a second layer, they repeat. So now you just have an, don't do this. Then you just have an exponential here. So you actually only have to calculate this. And you can do everything in a parallel. So actually, this is 60 measurements, no matter how many qubits you have. Because if you have more qubits, there's just more tiles that you do in parallel. And the second column is another 16, because everything can then be done. So then you are at 32, no matter how layered your QPS is, and how many qubits you do. Of course, it will get worse if you assume 5 layers and do it, but yeah, talk about this in a second. So this is the idea. This is the actual formula because it depends on if you have an odd or even number of orbitals, but this is in the end the actual matrix product reconstruction. There is now a little bit of a problem, and that is that you do remember the M0 is to do readout and the gate part. The problem is now we are characterizing the readout several times because we will do the readout here, and then we do it here, which has now the readout on these 2 layers again. And then if you have a second layer, you have all readout again. So you do a readout overcorrection. And we were like, that's of course not ideal. So we use a second quite strong approximation, and you're happy to challenge me on that. We just assumed the gate arrow part and the readout arrow part is a product. We assume that out of nowhere, and I'm very happy to agree that this is the case. Because then we can say, okay, the gate part, the pure gate part, is just the readout part as done by Bravi with no circuit, and the thing we actually measure. So basically, with our 32 circuits that we do with M0, now to another 32 circuits with just the pure RAM, we can reconstruct the full gate. And then we can have just one layer of tiled part that we add. This is kind of the formula, but basically you end up at most 64 plus 4, that depends on if it's even not, circuits to characterize it. And then it should in principle work. And then in principle, it's observable and it's dependent. We have an approximation of gate error, and the noise characterization in terms of constructing the M is now it's just now a constant thing. It's not exponentially scaling anymore. Of course, we have a locality approximation, and we have this noise channel approximation. And this is a function. Okay, so let's have a look how it actually does. So lithium hydride, 4 qubits, and we do electronic Hamiltonian, and we do up to 166 entangled gates, and this is now number of layers. This is always done with QPS, perfect pairing QPS, and we have here the number of layers, and what you can see in blue is the energy we would get out. So it's a difference to what we should get exactly, and you can see here an interesting but very obvious trend. In principle, the energy should get, of course, better, but if you have more layers, more error. And now, if you let them 0, or the actual M0 we construct the full matrix, you basically, your error goes down to 1 millihartry, 1 millihartry, under 1 millihartry, 1 millihartry, no matter how many layers. And surprisingly, and sorry, this is very important, I should have said that. That's for the noisy simulator. Very, very big caveat. Yes, you will. There is a white space for a reason. Very caveat. So basically, this error mitigation is very good at learning the noise model of IBM at this stage. This is all we can really say. We have kind of reproduced this the noise model. We are actually getting it down. So how does it look on real hardware? This is IBM feeds. It's not too bad, but so we see several trends. Number one, the raw results are much worse than on the noisy simulator. And this is always the case. The noise model is always better than the actual hardware. If anyone who's run something, compared these two, never seen the other way around. And now you also see what we expected more, that our approximation gets worse if you increase the layers and you have the exponential. But nonetheless, this is for 1 layer, 2, it's not too bad. We are correcting the error by quite a bit. Yes, how many shots? I can't tell you. I only can tell you timing. Sorry, but it's in the paper because that's kind of the thing which comes for a second. So we only spent 2 minutes on the error characterization of this M matrix because that's now very quick. All is done in parallel. You just have the 64 circuits. So we took 2.5 minutes in terms of measurements cost to do the tiled M0, and then 1 to 4 minutes or 1 minute, depending on how much layer to do the actual Hamiltonian simulation. I will show something a bit more bigger, which is that Butadiene, 8 qubits now for 450 entangled gates. Again, the simulator. This is the error we get on the simulator. This is how we get it down by using the error mitigation. And we did it on hardware, and we were quite surprised. It actually worked quite well. So we were from like a 450 millihartry in the raw results. We were now at 28. Yeah, that's not bad. It's not chemical precision, but we are, it's not bad. This is just tiled M0, nothing else. No error suppression, no post selection. It's really just this method. And now that's what I want to highlight is like, it takes 5 minutes to characterize it because as I said, it doesn't take much time. And the amount of shots we allocate here for now, this was just with some Höfting inequality. That was very hand wavy. This can be optimized to actually find the right value. We are not there knowing what's best yet. And then we went bold. And we thought, okay, now we've been seen in a 6 active space, 12 qubits, or almost 300 entangled gates. Again, we now know that we can learn the IBM noise model, but now we went to hardware. So good thing to highlight. Again, we only spent 5 minutes in the error mitigation. We spent 120 minutes on actually the expectation value simulation. This is very important to keep in mind. But we only reduced the error by a factor of 2. And that, of course, was a bit, sad, or discouraging. And then we thought like, okay, why? Why is this suddenly so bad? And this was manual pain. And then normally you should look at this list. So we spent 20 minutes on the energy evaluation, and here we spent 126. The reason we did this is a bit historically, but we use some, as I said, some equality to try to understand how long we might need. Probably would do it differently now, because then we looked at this. So what I show you here is we just took IBM phase and we just blocked it for 120 minutes, and we run some repetitive tasks that should always give the same result. And we run it twice. So twice we blocked 80 minutes. 2 tests. And what you see here is that we saw the chip on the noisy within shot noise, the same number. That was what happened on the hardware. So the problem is our time 0, yes, we can deal with trying to understand the absolute shift. No problem. I mean, not no problem, but like okay-ish. But that's not just noise drift, this is complete noise fluctuations. So if you do your time 0 characterization here, and then you run the experiment here, good luck. That was useless. Now you spend time for no reason. And this is of course a problem. So why was that so bad? Well, this was 120-minute experiments. Linux has had a lot of these spikes. So yes, characterized noise can suffer from error drift and fluctuation. We learned that the hard way. And so now we have to kind of find a way of maybe monitoring this. So you have to find a way, future problem. But you have to find a way of not doing something to say, you can monitor this. And then, of course, if you have too much of a deviation, you either recharacterize because the time still doesn't cost a lot to do, or you say, I don't know, and wait until it goes back up. We'll have to see. Something has to be done. If not, okay. Or I say we wait a few years, maybe the half gets better. It's always nice option, but it's not boring now.
To IBM say that, our hardware is probably good for this amount of time, and then, the noise jumps to the drift, or have they not?
No, I don't get that information. You have these like heat maps of the qubits, and then they do some characterization for one time, and you get updated ones. Maybe they internally do somehow monitor things. I don't know that. I hope they do. I mean, it wouldn't cost them anything to do. They could always run this.
Are you even being allocated the same physical like junctions every time here?
Yes, we took a second.
Okay.
Yes. Yeah. So when I said I blocked, we blocked. So like we had this.
But theirs is like some 70 qubit device or something.
Oh, yeah.
You could be here or you could be here.
Yeah, no, but we kept the layout. They kept the same transpilation.
Because they get quite a lot of variance between even those.
Yes, 100%.
Yeah, strictly to the ball.
Yes.
And do you have any idea if there's just other stuff going on the device at the same time?
I mean, no one else used the device at the same time. They don't do this yet. I mean, I don't know, maybe not half a Kelvin to warm. I don't know. You see, I don't know much about hardware. I mean, something happens.
One of the engineers walked into the room first.
Yeah, there was something.
Yes, they treat themselves.
Something happened. And I mean, it's good to know. And now we have an excellent tour. So we'll see.
Sounds like IBM problems work after this.
We showed this to IBM. They were like, I don't think this is probably people who work much closer to hardware than us would have told us that from the beginning. But we weren't aware. We knew of noise drifts, but we weren't aware of these spiky behavior. But yeah. Right. Is everyone happy with knowing how to run hardware or not run hardware?
Running hardware.
Yeah, I'm a bit confused about. So you're taking your optimum thetas, and there is an assumption here that your error model is insensitive to the angles of your gates.
Yes.
And you just have thrown that away, and it is a possibly quite large factor. Okay.
We are so the M0 is the thetas to 0. So basically Clifford version of your actual gate. Yeah, that is a huge assumption.
Yeah.
Because the actual thing we then run uses the optimal thetas. Yes.
You could have that as a parameter in this calibration. You could scan over a set of thetas.
Yes. I mean, you could try. I mean, we worked a bit on talking about this today, Clifford data regression.
Yeah.
is basically kind of doing this. I mean, you have a
fixed nodes,
yes,
configuration space, yeah.
You could think about more things. The thing here is the simplicity, because now we don't need a lot of time. It doesn't depend on the features, and we could run maybe a VQE. It is a very small one, maybe.
But my thinking there was because you have this really nice efficient way where you're calibrating the characteristics of a tile, you kind of could just add it as another dimension where you have a single tile and you scan over it and you're like, man, these are really bad features, these are really good, and maybe you get a better impression of this and that. I mean,
Yeah. I just I don't know what people want afraid to get pizza. I can also stop talking for a minute. All right. So probably the last thing I want to talk about is think about how we maybe can do this stuff, one state. So not just the electron actually is a beautiful servo, but actually not a servo. Now it's a nice characteristic to know the ground state energy, but maybe there's someone called experimentalists and they like stuff that they can actually measure in a lab. So the question here is how can we do spectroscopic properties on quantum computer? And so basically, how can we simulate that matter interaction? Yeah, so basically, you want to know stuff like absorption spectra or extended states, things that's important for industry-related fields, or like fundamental research, understanding of photovoltaic, light harvesting. We've all read paper introduction. So what's the idea of this algorithm? Quantum in response is basically do this as a measurement scheme. So we have we say we create a ground state wave function, and now we want to obtain spectra and excited state properties by basically constructing a subspace. This is quantum in response. It's called quantum in response because it's based on linear response theory of electromagnetic theory that existed for decades. I mean, there was just a special issue, 40 years, linear response theory. That's it. It's fun. We've done this. This is always optimized in adaptive and active spaces. So basically, we did a QSCI version of this. And I'm just going to very quickly kind of hand-wave explain what it is. So basically, if you want to derive a response, which you can do if people have done many times, you end up at this kind of a generous eigenvalue equation. So you have something that's called a Hessian, single derivative. You have something called a metric or an overlap. And then if you diagonalize this, you get excitation energies, and you get something like excitation vectors. If you do, probably people have done these decirculation or equation of molten coupled cluster, I don't know, something like this. Same thing. And you get excitation vectors, and there you can use to get some properties out. How are these looking like? These Hessians and metrics are basically big matrices where you have a ground state wave function, and then you do some kind of commutator expressions with the Hamiltonian, and then you have R and Q, which are R is the active space excitation. So if you do plus SCF in response, that's a full active space. And Q are your orbital rotations. So these are like, again, orbital rotations, which maybe within a space, but normally in like QSCI, where you mix your inactive and active space and active and your virtual space. These are the two operators. And you only put the active space on the quantum computer because you assume there's correlation, and this is done on quantum computer, and the orbital rotation are then basically quantum and classic in a way, because some part actually at quantum computer, on quantum, on orbital the active space. Okay. So basically what we've done, and we've formulated this in like a truncated active space. So quantum response singles doubles, that means we only allow single double excitations. We've also done that spin adapted because preserving spin is sometimes nice to do. But nonetheless, if you do this scales, and I want to say that this scales n to the power of 8. Because you do basically a CISD on top of basically a CISD on top of a ground state wave function. This is exactly what it is. And that just creates matrices that scale n to the power of 8. It's still more efficient than what has been done in the quantum literature before, which was called quantum subspace expansive singles doubles. They, when I said it's a CISD on top of the wave function, it was technically wrong. It is a linear response singles doubles on top of it, because that's exactly the difference. The CISD on top of a wave function scales n to the 12. This gets only into the 8 because you do the commutator expression, which is just the first order. We have something called rank reduction. You get rid of some of your commutators, some of your annihilation equation operators, and then you go down to the 8. But you don't get actual wavefunctions. Okay, I might go a bit technical now, but the point is you have to evaluate these kind of matrix elements on your quantum computer. You go to a Hessian matrix, you build your metric matrix, you do have a generalized problem, you diagonalize it, and now you can do anything you can do in the response equation of motion theory on that you know from traditional electronics theory. So some example, ideal simulator results, and I don't know, you can do the absorption spectrum here of benzene, 6 active space in a triple theta basis set. So important. So we have orbital optimization. So the class SCF version. So triple theta has an impact. It's not just we cut out. They are self-persistently optimized. Now this is a UCCSD, for example, and then you can see, I mean, if we do this quantum responses in orange, and in blue we have traditional quantum chemistry plus SCF in the response, and you can see the absorption spectrum is largely reproduced. You can do other stuff. This is always I always just like that example because that's electronic circuit diaprism spectrum that helps you to analyze theology. But again, it's something, it's just an observer you plug in into a response formalism. And again, the one you can get from traditional quantum chemistry in this setup basically gives you the same, which was to be expected. But it's nice to at least test it. So again, in principle, this is something that allows us to divide the measurement protocol on a quantum computer and then gives us into our 8 costs. Then we tried this on a short noise simulator. Now, core level absorption spectrum of water is also something that's interesting. This is now a short noise simulator with what you see here going from top to the bottom is what you expect to see. This is the ideal spectrum, meaning the spectrum you get from class SCF in the response, being also from our quantum response colors. And in the light blue colors, it's just 20 runs on an actual short noise simulator with that many shots, that many shots, and that many shots. And what you can see, I mean, the better your statistics, the better you reproduce the actual spectrum. I mean, there's nothing unexpected here. It's just
So when you're actually sampling the Hessian and the
so you are sampling all the elements in Hessian metrics, and there is a reason. You can see that some peaks, like this one, is much more susceptible to the short noise, and that's because it's not as simple. You sample because every element in your Hessian has a standard deviation. And every element in your Hessian can also be, in principle, a classic element if it's in public inactive and virtual. It can be an inactive active, which has only 2 annihilation equation operators acting in the active space, or it can be a double excitation in the active space. So completely different variants, completely different elements. If you do a general triangle solving of that, it's far not a trivial how this impacts each exact state. Yeah, I mean, this is 100,000 shots. It's not velvet, I admit that. That's 100 shots per click head. So if you do QVC, that's for one commuting group QVs. There are a lot of commuting groups. So that would be 80 million shots overall. So that is, there you see the end of the power phase scale. And then we run it on IBM again. That's a while ago. In Osaka in 24 with M0 again. And we run 5 times. And you can see here it's overlaid, and here these are the simple ones, the 5 runs. And you can see exactly what we saw the short noise simulator. Some peaks we are very nicely reproduced, and some others you can see this large spread in where the peak location actually is. Because we have no short noise, and additionally we have device noise. Proof of concept. It was the first thing I've ever myself run actually on a quantum computer, so it was just this initial excitement of running on a quantum computer, and then
You've added no additional broadening here that just comes out from the.
No, this is broadening. Yes, the linear response theory. Sorry, is just giving you excitation energies.
Yeah.
So you then do this Lorentzian Gaussian fitting with certain you do in any other theory. It's not. We have a paper on damped response as well, but it's I'm not going to talk about this today.
So can you sort of can you make assumptions that the noisier peaks or noisier excitations are most likely the samples where there was something pure quantum.
Yeah. So you can look in this paper, and there's a lot of explanation on that.
Yeah.
Yes. So why do some peaks move a lot? But the hand wavy thing is yes. They are dominated, for example, by active space double excitations in there, and then they are much more susceptible to variance. Oh yeah, so this was with M0 before we had tiled M0. So that took a lot of time. We invested a lot of time here, 18 minutes. And okay, this is sometimes I like to show this. Yeah, if you would have paid for that with the IBM K as your go rate, which is I think $96 a second, you would have every spectrum would have cost you a bit over £4,000. Sometimes fun statistic show. He didn't pay that obviously. Keeps my okay. We have extended this. I'm not going to talk about any of this. And from the people in the room, the chemists were screaming to me, why are you constructing a Hessian? Of course, no one in quantum chemistry would explicitly construct a Hessian. So what you can do is you can do what's called a Davidson solver that's done in any electronic structure theory code. Always. We've done all this with quantum suspect. It doesn't matter. So basically what you do, you don't explicitly construct the Hessian, the metric, but you create the Hessian vector products and then iteratively solve it. What that means is you start with some guess solutions, and then you calculate how these guess solutions contract with your Hessian, for example, and then these kinds of elements, and then you're iteratively trying to find a solution. And no matter how many guess solutions you do, you get that many solutions out. So basically, you basically only calculate a little bit of your Hessian matrix. You also obviously then get less states out. Like if you do an explicit Hessian construction, you get all states out, but people are rarely interested in the first 5,000 excited states. So normally you do this, and then this is basically the element on the quantum computer. You can actually calculate that. We done it on the Dogma simulator only. But there was a fun thing that this actually also reduced the scaling to the n to the power 4. It's quite cool. With a huge prefactor, but students can now get. Well, this is really nice. This is doable, I would say. Peter has also done this with polarizable embedding. Again, which was structure theory people know this can be done. You can do based on motion covered cluster, linear response theory with an embedding potential in it. That's just what we did as well. And then you can have like the effect of an environment on it. Yeah, it's just another one addition operator in your framework. Yeah, a lot of cells. This is so this is one way to do it. It's an interesting way. I mean, you can clearly see that we are traditional quantum chemists working on a quantum computer, because that is like this is like what has been done. And this is some people call sometimes probably the Danish school. Like this is what has been done. I mean, this is very established. And but nonetheless, it works. I think n to the power 8, of course, has quite hefty scaling. But in the end, it's also not a simple thing, because you have some kind of correlated states on top of ground state where you want to extract from. I mean, it's not a simple problem. But you can also try to do it differently, which is that actually uploaded today. But instead of framing excited states as a measurement problem, you can just frame it as an optimization problem. Because that's a clever idea. You have to judge for yourself. But basically, you do something that's called like state average in QE, which is the same like state average plus SCF, multi-state SCF, what you know from compactness theory. Well, it's not actually the same, but it's similar. So basically, we are trying to find an ansatz that parameterizes several excited states, several states at the same time, and then we minimize this. And this has been done before. We just did this again with orbital optimization. It's been adapted in spaces and some other things. And then in principle, you get explicit excited states or explicit states expressions that you can also put on the quantum computer for all the states you ask for. So basically, you're optimizing the trace for multi-state Hamiltonian. Would be the correct, the explicit thing to say. That's of course hard optimization. If you think VQ is easy, try state average VQ. That's another idea to get excited states in this framework. So the work here. So basically, what you do is you define yourself some initial. You define your states with some initial reference, some complicated state functions. You say, I don't know, alpha is probably a good guess, and then like a single excitation, double excitation. Do this spin adapted because it's a good thing to do. And then you minimize that. And then you have to do something called state resolution. So this optimizes the trace. So if you then want to get the actual excited state out, you have to build these kind of multi-state Hamiltonian. This is basically the full Hamiltonian between all excited states. And if you diagonalize that, you can get expressions for basically how to construct each state on the quantum computer. And then you can actually construct the state. I mean, this is like an electron structure theory. Response, equation of motion gives you the response, the first order perturbation for an excited state. This gives you the actual excited state. It's just like if you do coupled cluster or state average coupled sphere. And you can get properties out of it. Because I mean, now you can calculate anything. Even operator sentence can state and we calculate it. It's the same, it's the state problem. No matter. There are some details on how you actually do this on a quantum computer. Because we always try to actually do it on a quantum computer, and then you will realize that there are some problems. So to calculate these elements, you have to do some kind of superposition trick to actually get them on the quantum device without needing a Hadamard test. Because naively looking, you would think Hadamard test, and you don't want to do that. But under certain circumstances, you can propose it like this, and you can in principle do this in the CSF basis, or you do it in the determinant basis. And this is more measurements, but shorter circuits, because the gate preparation is simpler. Whereas here you have to create a superposition of CSFs. What I actually want to show is now we've done it on hardware. This is an IBM Marrakesh. This is what's done very recently. For formaldehyde, reactive space, 6 qubits, 4 average states. So we have a hard fork, spin adapted singlet, another singlet, and a double excitation. We use it's a 78. Now you're going to ask me which answers, because I'm asking myself. I think it was QPF. I should have put that there. And use the F0 as always. And you can see here the absorption spectrum of the first bright state in formaldehyde. And the row is also here in green. And then with the M0, get a bit better to what you would expect in the noiseless. But again, this is now just playing around to see if you can actually, with other algorithms, you're not, yes, not if you actually can bring it on a quantum computer. And so we always test it if you can actually bring it on a quantum computer. Yeah, okay. Let's talk about this. So for the light. Yeah. So other questions to move out, right? And over there again. Yeah, thanks, Nico. So of course the people in Southampton, my group, and we had fun in they probably hate me showing the picture. We had fun in a study room. Successfully got out. If not, I wouldn't be here. Get ready, yeah. I want to thank the other PIs in the Danish quantum project and collaboration partners, and of course, people and companies who supported this work, and especially Novo Nordisk pays for the hardware access. Is that $4,000? There's so many questions. Are there more?
If there are no more questions, then we can stop the recording here and
Questions.
yes, and then people can ask all the secret questions.
Yeah,